Hello everyone, I hope I'm audible. Okay, okay. Hello, my name is Archita. I am a PMRF scholar at ISER Kolkata. Now, today I'm going to take session 2 for the second week lecture series. The purpose of these interactive sessions is to find some questions that could be relevant and then to solve it online. And if you have any queries in between, you can ask me. uh, okay, so let's start. So this is for the course Air Pollution and Control. Okay. Now, in this lecture series, Sir has talked about different sources of air pollution, natural and anthropogenic, and point sources, like moving sources. Hello. Can you please turn off the mic, Saundarya? Okay. Sorry. Then Sir also discussed about the visibility, how haze affect the visibility. Then we discussed in the lecture, there is a discussion about albedo and the effects of warming and cooling, effect of different air pollutant on the warming and cooling of the atmosphere. We also discussed the different lapse rate, their effects on the stability of the atmosphere. Yeah, sure. Okay, okay. Is it now? Okay, sure. Okay. Wait. Yeah. Okay. And then in the lecture series, there's a discussion about the general circulation, the atmospheric inversion that happen in the atmosphere. And so we'll touch upon all of these topics one by one via questions. And let's start. Okay. So first is haze. Okay. Yeah, sure. Tell me. Hello. Okay. Who's talking? No. Okay. So visibility. So when we discuss visibility, we know that in the atmosphere. Okay. Who is this person? Uh, I- okay. Uh, Visibility is when in the atmosphere we see, especially this phenomena we can see in Delhi, because the air is so much polluted that we cannot see clearly anything, like not even the number plate of car in front of us. So visibility is when the air quality or the contrast between the object, like to identify an object, it becomes very difficult. Right. Now, the reason that the visibility of the atmosphere get affected is because of haze. Okay, so haze is nothing when the air particles or the air pollutants interact with the sunlight and the water vapor. They create uh, this sort of structure which actually leads to depletion in the visibility. Right. So nothing but the when the pollutant interact with sunlight or the sunlight and the water vapor or humidity, you can say. So they form this layer sort of which leads to decrease in the visibility. Now there are different type of haze. So first question is about that only, that what are the different type of haze that we see in the atmosphere. So these are plume haze, layered haze and uniform haze. Now, as the term suggests itself, let's say there is a factory, okay, and it has a shaft. Now, sometimes when the particles are released from this shaft, they generally, in the form of flume, they make this sort of structure, and the visibility is only reduced in this region, and the area outside of it is basically clear, right? So that is plume haze, that only the particles, like only the particle that is coming from the shaft of a industry or of a power plant, those particles come in contact with the sunlight or the humidity or water vapor, and make this shield or sort of structure, and reduces the visibility in a particular region of plume, right? But sometime, if let's say the number of industries are more, or the dispersion is high, then what happened that this these plumes from these industries, they are generally in the form of a uniform layer. So that is layered haze, that when uh, the haze is in the form of layer, okay, and then you can clearly see that, okay, this region is hazy, and the above it, it's clear, okay. And the third is when the haze is uniformly distributed in the entire atmosphere or the visible region. The best way to experience different type these different type of hazes, when we go into mountains, okay. So because of the valley, so we can see these different type of phenomena of haze very clearly. In Delhi, generally what we see is uniform haze. Okay, we don't see this plume and the layered haze. But when you go to valley and mountain region, you see these plumes or these layered haze very clearly. Okay, so these are the three different type of haze that is found in the atmosphere. Now, how this haze affect the visibility of the atmosphere? That is the second question that we are going to address. Okay, so uh, haze haze is nothing but particles interacting with the sunlight and humidity, and they make this path sort of structure which reduces the contrast, or which reduces the visibility. So what happen is that these particles can have absorption as well as scattering, okay. In the last class also, I said that there are certain particles, for example black carbon, brown carbon, they greenhouse gases, they actually absorb light. And on the other hand, there are particles like sulfate which scatter light. Now in this haze, the particles that are coming from these chimney is not necessary will not necessarily be of one type, okay. It is not like only black carbon is coming from the chimneys, or only sulfate is coming from the chimneys. They are mixture of both absorbing as well as scattering particles. And due to this mixture, some particles absorb light and some particle will scatter light, and leads to this reduction in the visibility. Okay, so that is these are the two phenomena which affect the visibility. Now, later we discuss the albedo. On the effect of albedo on the surface. So, to understand it, first we need to understand what is albedo. So, albedo is nothing, just reflectivity. That is how well a surface can reflect the sunlight back, is its albedo. Okay. Now, albedo changes from material to material. Okay. So if it's a snow, it has different albedo. If it is water, it is different. For land, it is different. Okay. So for different surfaces, the albedo changes. The reflectivity, or you can say how the light like interact with that surface changes, right? So this is what I have, this is a table I have put here, which to understand that how the albedo change for different type of surface. Okay. uh, Wait. So how albedo changes for different type of surface. For example, for a cloud, it's about 50 to 90%. They are highly thick clouds are highly reflective. Snow is highly reflective, right? On the other hand, water, grass, other surfaces are less reflective compared to it. Now, this albedo actually get affected by the air pollutant. The air pollutant can actually affect the albedo of these surface, right? For example, if for the, let's say, snow, right? In a snow surface, if there is a deposition of absorbing aerosol, and one of the major absorbing aerosol is black carbon, let's say, on a snow surface which has a very high reflectivity of about 50 to 90%, then when on this snow, let's say, a thin layer of black carbon got deposited because of industries or vehicle or whatever, let's say. Now its albedo is reduced. Okay. With increase in the pollutant deposition on the surface of any reflective or reflective surface, there is increase in the sorry there is a decrease in the albedo or reflectivity. And now this decrease actually create a positive feedback loop. So this loop that you are saying, it's a positive feedback loop. What is a positive feedback loop? That when, let's say, a decrease in one thing leads to further decrease, okay, or an increase in certain things leads to further increase, that is a positive feedback loop. That is, an increasing thing leads to increasing increment, and a decreasing thing leads to a decrement. So in the same sense, the more the pollutant deposit, the albedo decreases. As the albedo decreases, this snow start melting. As the snow start melting, the sea level will rise, and hence uh, further this cycle will start. Okay. So it's same that if the albedo decreases, this surface become what? So generally snow is deposited on either a land or water or grass. So water has 8% albedo, grass has 10%, right? Forest has 15%. So if, let's say, on a water surface a snow is there, and it has a very high reflectivity. Now the black carbon is deposited on that snow. Its albedo decreases, its reflectivity decreases, it start melting, and then what we go towards this water, which has a lower reflectivity. So it creates this positive feedback loop. Now, uh, next question is about the warming and cooling of the atmosphere. As I said, that there are certain uh, aerosols, or sorry, air pollutants which are absorbing. There are certain air pollutant which are scattering in the atmosphere. Right. Now, if we know that anything which absorb sunlight, what will happen? Okay. For, in a simple manner, if we say, let's say a black t-shirt, okay, or our hair, like black hairs, what happen? It absorbs the sunlight, and it becomes warmer. So whatever absorbs the sunlight, what happens to it? It warms the atmosphere. And whatever reflect the sunlight, for example white clothes, okay, simplest example is white clothes. So whatever scatter the sunlight, whatever reflected back, leads to cooling, right? So those aerosol or those particles which scatter light, they leads to cooling of the atmosphere, and those particles which absorb the light leads to warming of the atmosphere, right? So answer is same, that the absorbing and the scattering particles are the reason that something is warm or cool. Now, to explain it further, uh, sorry, just a second. Okay, so this uh, I have. Okay, so this figure is from the lecture only. So zero is that neutral is neutral. Negative means that, hello. Negative means that the temperature is decreasing, and positive means that the temperature is increasing. Right? If the temperature is increasing, then it leads to warming, and when the temperature decrease, it leads to cooling. Okay. The, okay, wait. It's not with. It's. Uh, yeah, yeah, sure. I'm zooming it. Now is it visible? Okay. Okay. So this is forcing. Hello. Can can you, whoever is talking, can you please mic turn off the mic? Thank you. Um. Okay. So forcing can be. Okay. Um. Uh, So forcing can be positive as well as negative. Positive forcing means that the temperature is increasing, and negative forcing means that the temperature is decreasing. Right? When temperature decrease, it leads to cooling. When temperature increase, it leads to warming. So this side is positive forcing, and this side is negative forcing. Now there are different particles that are shown, uh, and their effect on the radiative forcing of the atmosphere is shown. Okay, so let's start with CO2. CO2 is one of the major greenhouse gas, and it has a longer lifespan. Therefore, it leads, and it shows what? It shows positive radiative forcing. It means it leads to warming of the atmosphere. Similarly, methane, okay, it's a halocarbon or a hydrocarbon that release one of another greenhouse gas. Again, it leads to warming. That is why greenhouse gases are so much, like, they are bad to look on, because they leads to warming of the atmosphere. Now, another is ozone. Ozone can be good and bad. Okay. um, so good ozone is ozone that is present in the stratosphere. It has almost negligible effect uh, on the forcing. The bad ozone is the tropospheric ozone, which actually can leads to warming. Okay. Then water vapor also could leads to warming. Then comes the black carbon. Now, what shows here is black carbon on the snow. So this black carbon leads to warming, because as I explained earlier, that when it is deposited on the snow, it reduces its albedo or reflectivity, hence initiate a positive feedback loop, and this positive feedback loop hence leads to further further warming of the snow. Right? Now, there are other effects that has been discussed here, which is the direct and the cloud albedo effect, which we'll discuss in the later classes. Okay, these are nothing but direct effect means that when a particle directly affect, it means that, for example, again, a black carbon is a particle, not a gas. It's a particle. It directly settle on a surface and absorb light. Right? That is direct effect. When a constituent or a pollutant is directly participating in the warming or cooling. Right? Now, second is cloud albedo effect. When the particle does not directly affect, okay, it's not directly absorbing, this particle leads to different processes. Okay, let's say this particle decreases the cloud albedo, and hence this decrease in the cloud albedo uh, causes the positive forcing. Okay, so when a certain pollutant directly cause the warming or cooling is direct. When it affect another phenomena in the atmosphere which causes the warming or cooling, that is a indirect or semi direct effect. And this cloud albedo is one of the indirect effect of any aerosol. Okay, so these are the these are some things that we need to know, that there are a lot of particles in the atmosphere which actually are warming. And now the lifetime varies. Okay, for example, black carbon, brown carbon, they have lifetime of 7 to 10 days. And the and methane and carbon dioxide, they have lifetime in years. Okay, so when you say 7 to 10 days, it means that if I stop the all the sources of black carbon or brown carbon today in the atmosphere, okay, within 7 to 10 days there will be no absorbing aerosol. Okay, because two absorbing aerosol, which is black and brown carbon, we are completely negating, because we are shutting down all the industries, all the power plants which release this. So on the other hand, things or the pollutant which has longer lifetime, for example carbon dioxide, methane, they need strategic plans which the government agencies and the policy makers are trying to make, because they need strategic plan to for longer duration, for couple of years, like 10, 20 years, 50 years, to remove them completely, like if we want to. Okay, that's why these days the study is more focused on the short-lived pollutant, so that at least we remove the ones which are short lived, or at least we reduce the one which are short-lived, right? Next is maybe move towards the another question. um, okay. Um, Next is the relation of carbon dioxide, temperature, and ice. So, as I suggest earlier, that carbon dioxide is increasing every single day. Now we have to see that how this increase in carbon dioxide is affecting the temperature, and hence affecting the sorry, the ice in the glacier, and which in turn affect the sea level. Okay, so again it's also an example of positive feedback loop, that increment in one thing leads to further increment in the all the other things. Okay, so here if there is an increase in CO2 which is happening, okay, or any other absorbing aerosol, it leads to what? Warming, hence increase in temperature. Now if the temperature is rising, okay, for example, let's consider for now it's CO2. Okay, now why CO2 is greenhouse gas? Because if there is CO2 in the atmosphere, let's say this is CO2, okay, now there are two types of radiation in the earth. One is the incoming, another is outgoing. Let's say this is earth surface. Now there is a inflow of radiation from the sun, and there is an outflow of radiation, right? Now what this CO2 does is that when the radiation, the infrared radiation, is going back towards the out of the earth towards the sun, it traps it. Okay, this CO2 trap this infrared radiation, this outgoing radiation, and hence increases this temperature. Sorry, this temperature increase is actually one of the cause of the melting of the arctic ice. Okay, now whenever the ice melt, what happens? So we know that in the earth there is glacier, there is land, there is sea, all of these things. So, and in general, near a landmass there is always a sea, right? So if this is a land, there is always a sea nearby it. So if, let's say, the glaciers are melting, what will happen? There is increase in the sea level. Okay, So the sea level will rise, and if the sea level rise, what will happen? The coastal habitat, okay, the buildings, the people, everyone who lives near coast, their life will get affected because of this sea. Okay, sea level rise. So the so this increase in CO2 actually is again causing this positive feedback loop of increasing temperature, increase in the glacier melt, and hence increase in the sea level rise, which in turn affect the sorry, which in turn affect the people, right? Now after this discussion, there is so this air pollutant not only, they not only affect the air, the sorry, uh, they are not confined in the air only, okay, they also affect the soil, they also affect the water bodies, they also affect the marine habitat. Okay, so we'll discuss it also. For example, so next question is about that which type of soil is resistant to acid rain. Okay. Now we know that a soil is good. What there are different characteristics that define that a soil is good or bad. Okay. For example, its water holding capacity, that how much water a soil can hold, its salinity, okay, its nutrient contents, and its pH. If a soil has good parameter on these four characteristics, then we can consider a soil is good. Okay. Now the acid rain, which is nothing but sulfate and nitrate acid mixed with the water, they affect the nutrient content, the pH, the salinity, and the water holding capacity of the soil. But there are certain soil which are actually resistant. Okay, resistance mean that they have certain compounds in it which help them to not get affected by the acid rain. Now, since the answer is calcium carbonate, but why it's calcium carbonate, let's see. So first is, what calcium carbonate is? Base. Okay, it's basic in nature, it has a high pH, and acid rain has a low pH. So anything, any soil with a good basic content, okay, it balances out the pH. Next is the nutrient. So this calcium carbonate, when react with, let's say, SO2, it leads to formation of calcium sulfate. Okay, so this SO2, instead of leading to formation of H2SO4, this SO2 form the calcium sulfate in the soil, and hence the nutrients will be stable in this type of soil. Okay, so it balances the pH, it makes sure the nutrient are not going anywhere, and hence this type of soil rich in calcium carbonate, is actually resistant to acid rain. Okay. Uh, Now next is the effect of water on the of the air pollutant on the water content, on the water or marine life. Okay, so in certain location we see that, uh, for example, I don't remember correctly, but I have seen this in one of the documentary, that in one of there is a sulfur mine in somewhere in outside India, and this sulfur mine has a very high content, like it has this yellow liquid that comes out of it, which is a very highly sulfur rich liquid, and this liquid actually has destroyed all the marine life nearby that water body. So why? Because this liquid has high content of sulfur and is actually highly acidic, very low pH, and this cause the issue with the hatching of the larvas, or for the survival of the zooplanktons, phytoplanktons, all of that. So this is acid shock. Okay, that when, let's say, when in a normal or calm water there is a sudden entry of acid rich compound or acid rich water or snow. Okay, so if uh, this this can comes from mines. Okay, if there is a sulfur mine or any mine, or this can come from the atmosphere. So this acid so this sudden enrichment of acid to the water system is called acid shock, because there is a sudden change in the pH of water, there is sudden depletion of the nutrient, there is sudden sorry, there is sudden deaths of fisheries and marine organism in the water body. Okay, right. Now another effect that that air pollutant can have on the water is eutrophication. So what eutrophication is, that when in a water body there is increase in the production of algae. Okay, if it happens mostly in stagnant ponds or lakes, but in general in a water body, if there is increase in production of algae, there is a lot of formation of algae, or algae is multiplying and growing very fast. So in that region what happen is that over water there is a layer of green color algae start forming. Okay, so what happen is that it cut the oxygen supply to the fish. So this once this oxygen supply is cut, these fish start to die, and hence this pond or this water body becomes like rich in these dead fish, dead plankton, and it becomes like a complete waste. So now why this algae start growing on the water surface? What this water has that leads to the growth of algae? That is nitrogen. So if a water body has high content of nitrogen, then these algae will take up that nitrogen, start growing, and make this surface on the water body and cut this oxygen supply. That is eutrophication. When the oxygen supply is cut, leads to death of fish or marine organism due to the overgrowth of the algae. Okay, so these NOx or nitrogen is the reason of the eutrophication or the enrichment of algae in the water body. Okay. Uh, Next is marine aerosol. So they are a type of natural aerosol. Okay. So we know that, and in this natural aerosol there are a lot of salt, right? So sea salt, for example, chloride, sulfate, all of these salt actually contains these chloride sulfate ions, and hence uh, they actually are corrosive. That is why the buildings or like the steel or aluminum or metal things near a sea or a marine body actually corrode very easily because of these chloride and sulfate salt in the aerosols. Okay, so we learned that the marine aerosols are corrosive, right? Now they can form or they can disperse in two ways. So these are the way of dispersion. uh yeah, like please turn off your mic, whoever it is. Okay, okay, so these are way of dispersal. They can either disperse in the form of jet drop, or they can disperse in the form of film drop, right? Now the difference between the two is the angle. Okay, so this picture has said that film drops are in all the directions. So when the aerosol bubble burst, the particles or these chloride or sulfate particles will go in all the direction. Okay, On the other hand, in jet droplet, there is a unidirectional movement. In one direction only, there is a movement of these aerosol. So, like, if I ask you which one of these is more harmful, or has which of these dispersal phenomena is highly corrosive, the answer would be film droplet, because they goes into all the direction, right? Okay. Now let's move towards other questions. Uh, yeah. Now, sir also discussed about the different primary and secondary pollutant, then criteria pollutant and hazardous pollutant. So, I discussed this in last class. I will just revise that primary are one which directly formed by incomplete combustion, directly formed particle via incomplete combustion. Okay. Secondary are when there is a transformation, okay, when the particles are released in the form of gas and they convert into liquid or solid particles, okay, that is secondary. Third is criteria pollutant, okay, and fourth is hazardous. Hazardous is a pollutant which are harmful in even the slightest concentration, right? Now what the question is, what are criteria pollutant? This is very important because these are the pollutant that are actually acknowledged and by the EPA, which is Environment Protection Agency, or NAAQS, which is National Accreditation of Air Quality Standard, and they have actually decided on uh, these criteria pollutant and their threshold limit. Okay, so criteria pollutants are that they are okay, like our atmosphere is okay with them up to a threshold limit, and once that limit is crossed, they become harmful or hazardous for us. Okay, so let's say in a region, like let's say in a rural region, pollutant are let's say particulate matter concentration is, let's say, 2 microgram per meter cube. That concentration is very low, but if that concentration become 100 or 120 200 microgram, then that concentration goes beyond this threshold limit and becomes harmful. So these criteria pollutants, 6 are major. There are others also, but major are ozone, carbon monoxide, sulfate, nitrate, particulate matter, and lead. Their threshold concentration have already been decided by the NAAQS and EPA, and if they goes above a certain limit, then they become hazardous. Now also another thing is that their concentration varies, okay, so their concentration for worldwide is different, and their threshold concentration for India is different. Okay, and country wise it varies depending on the pollution. Okay, for India the threshold limit is actually higher compared to other countries. Okay, now these pollutants, they have different processes of formation and transportation. These are the processes I will discuss in brief. Okay, volatilization is nothing but gas to particle conversion, gas to liquid, or या फिर or gas to solid. So when a particle or a air pollutant which is gaseous in nature, sorry, it's other way around. Okay, so when the particles or they are formed in the form of gas or liquid or particle, whatever, these pollutant can easily because of their sorry, because of their low vapor pressure, they can easily become volatile. Okay, that is they can easily turn into gas. That is its volatility. Next is absorption, that how well a gas is absorbed on a liquid. Okay, adsorption, when a gas is stuck to a solid surface, it or a liquid got stuck to a surface, it is not entering into the particle, it is just make a coating outside it. That is adsorption. For example, some of the particles, when you understand the secondary formation of these particles, we see that they start with a tiny nuclei, and all these particles, sulfate, nitrate, water vapor, black carbon, ammonia, all of these start sticking to this one nucleus of any pollutant, and they make a bigger pollutant. Okay, so they are not mixing with the particle, they are only adsorbing on its surface. Okay, in other cases, they become part of the particle. Okay, they attach itself to the particle and form a different particle. They form a different particle by absorption. Oxidation reduction is nothing that there are certain metals in the atmosphere. Okay, they can gain electron or lose electron, right? So via gaining and losing electron, they can oxidize themselves and reduce themselves. That is another way metal can exist in the uh, atmosphere. Ionization is same, that sometimes a particle can have only radical. They can ionize by interacting with other particles. Hydrolysis is interaction with water. Photolysis is interaction with sunlight. Metal catalysis is nothing, there are metal which interact with the oxidant sometimes, and they enhances the process. Okay, for example, the simplest example is ozone. So in the formation of ozone, we always write this m, and this m is nothing but this metal catalysis particle. Okay, so I discuss them in brief. Now these transformation methods that we discuss, there are different ways a phase can be transformed, right? So we know that there are three major phases that we discuss in chemistry: gas, liquid, and solid, right? So a particle can be released in the form of gas, it can be released in the form of solid, it can be in the form of gas. Now uh, they can interconvert among themselves to form different type of particle. Sorry. Okay. Okay, so they interconvert among themselves to form different type of particle. So the phase transformation could be gas to liquid. Okay, gas to gas, gas to solid. Okay, gas to solid is sublimation, right? Then gas to liquid to gas. Okay, the simplest example is, so I will give you example of all of this, like simple example to understand. Another is gas to liquid to solid, and then solid to liquid to solid. Okay, now gas to gas means that a particle is released in the form of gas, it convert to gas. Okay, simplest is that NO2 is released and it converts to NO3, let's say. Okay, so a gas becomes gas after transformation. Sorry, NO3. Gas to liquid means that NO2 becomes HNO3 and becomes acid rain. So this is example of gas to liquid, when a gas converts into liquid. Okay, gas to solid means that a gas condense on react with a particle and form a different particle. This example of this is that there are a lot of VOCs in the atmosphere. They react with nitrate in the atmosphere and leads to lot of these what do you call PHs, uh, and nitromatic lot of PHs, let's say. Uh, And for example, the xylene or like alpha pinene, like there are a lot of, I will not go into detail, but there are a lot of pHs which form via this reaction, and pHs are solid. They can be solid. Um, okay, right. Then example of gas to liquid to gas is uh, that when a particle at okay uh, let's say hmm, let's say this wait okay, so this gas can, uh, can become liquid. Okay, so how it becomes liquid? If it has a uh, high vapor, it it becomes condensed due to its vapor pressure, and then again the vapor pressure changes and this gas again becomes the convert into itself. Okay, simplest is that the VOCs that are in the atmosphere, some VOCs can actually this is benzene, so some of the VOCs uh, can condense or can liquefy, and then once and then further becomes the gas. Okay, so it depends on its vapor pressure. Next is gas to liquid to solid. The simplest example is that sometimes what happen is that when these particles make the external mixture of air pollutant, let's say this is a nuclei on which gases are sitting, SO2, NO2 are sitting, and then it forms this rain droplet. Okay, and this rain condense on a surface, and the water vapor removes and only the particle settles. That is example of gas to liquid to solid. Okay, and solid to liquid to solid is again a particle get wet deposited, a particle get wet deposited. Okay, so this is in the form of water droplet. There is liquid and solid, this water remove and only solid left, that is solid liquid solid. So these are different phase transformation that can happen in the atmosphere. Okay, some are like some are very simple, some are actually very complex heterogeneous reaction that happen. Okay. Now, photochemical smoke is one of the example of such type of transformation, let's say. Okay, so again, um so photochemical smoke is nothing but a brown clouds formed due to VOCs and NOx, या nitrate reaction. Okay, um, so we have nitrogen dioxide. There is aldehyde can be from these VOCs. So this nitrogen dioxide in the presence of sunlight and water can either form HNO3, can form peroxyacetyl nitrate. These hydrocarbons are these VOCs. It can also help in formation of ozone, and these all the particles. Okay, whatever the NO2 is forming after reacting with VOC, they actually form a thick brown layer on the surface, and that layer is called photochemical smoke. So basically this entire thing, this brown cloud like structure, is only due to two major things. One is VOCs that are released from the forest and as well as anthropogenic sources, but major is the plant and the forest fire and agriculture residues. Um and NOx, which is there in the atmosphere. Um, and the important thing is that these phenomena are majorly towards the evening. Okay, you can see it towards the evening. The reason is very simple, that if you call it day and night, okay, so this is 0, this is 24, 23, let's say. Okay, we see that because for the ozone formation you need sunlight, so ozone is highest towards the daytime, towards the afternoon, and this NOx is highest towards the early day and the late night. This is NOx. So because the NOx is higher towards the evening, because what is happening is that the NOx, uh, so this is ozone, sorry. So the formation of ozone is utilizing the NOx. So you won't see the brown clouds towards the afternoon. No, you will see it towards the late evening or early morning, because the NOx concentration are highest towards that time, and VOCs are already there in the atmosphere. They react and form these other compounds also, the uh, PAN and aldehyde, all these other uh, component as well, and leading to the photochemical smoke. So these two are the major precursor for the photochemical smoke. Now there is discussions on the general circulation model and in the lectures. So before that, we we'll discuss about the OH radical. So OH is one of the major oxidant in the atmosphere. Now what we call as oxidant is anything which oxidize the air pollutant in the atmosphere, right? So there are certain oxidant that we count upon. They are OH, NO2 and ozone. Okay, and OH and ozone are majorly towards the daytime. So OH is actually one of the major oxidant because of its small lifetime. It has lifetime of seconds. Okay, so once it's formed, if it doesn't react with anything, it disappears. Okay, it forms water vapor. So it forms very fast and it reacts extremely fast. So this is major oxidant in the atmosphere because of its its rigorous cycle, and it reacts with almost every air pollutant in the atmosphere. You name it, sulfate, brown carbon, all of VOCs. It reacts with everything. So this is one of the major oxidant in the atmosphere. Now why it is scavenger? So scavenger means that it help in removing. Now it does not remove the air, all the air pollutant, no. It help in removing the metals. Okay, so it reacts with metal to form their oxides, and these oxide will be removed or will come down via wet or dry deposition. So this oxidant, no one else actually play a role of scavenger better than the hydroxyl radical. So hence this is one of the air pollutant which is an oxidant. It oxidize components in the atmosphere very fast, and it also helps in scavenging of metal in the form of oxide. Okay, and their deposition. Okay, now we look at the next question is about what are the cells in the general circulation model. Okay, if we study the circulation model in the atmosphere, we see that before this three cell, there is a one cell model and there is a three cell model. Hmm, okay, so there is a one cell model and a three cell model. One cell model is only based on the headley cell, I think it's in 1700s that this model came. And another is on the based of three cell, which is Headley, Ferrel, and Polar cell. So this one cell model is simple. What it says is that in the equator region, because equator is nearest to the sun, the air is warm. Okay. Now warm air means low density and hence low pressure. Okay. So if we know that density is inversely proportional to temperature and density is directly proportional to pressure. Okay, so warmer the air, that is higher the temperature of the air, the lower is its density and the lower is its pressure. Okay, so if uh, an air is less dense, what it does? Okay, anything which has less density, for example, helium balloon. Okay, what it does? It rise. So the Hadley cell concept is, since the equator is nearest to the sun or receive the maximum sunlight, it has the warmest air, and this warmest air, because of its because of its low density, it rises. Okay, and it moves towards the pole. And in the pole, because of low temperature, it makes a high pressure zone and a high density zone. Anything which is dense, what it does? It sink. So the cold air will sink and come back to the equator. Okay, so the hot air will rise and the cold air will sink towards the pole. So this is a one cell model of the Hadley cell. But later it was decided or it was studied that it cannot be that simple, that the entire air circulation in the entire globe is based on this one cell. So this was further divided into the three cell models. Okay, so what does this three cell model cell is says that, let's say the cell near the equator, which is 0 to 30 in southern and northern hemisphere, we call it Hadley cell. Okay, now it's same as discussed in the in the first model, that warm air will rise from the equator, it moves, it reaches 30-degree latitude. Okay, now it reaches 30-degree latitude, because it start getting cool down. As it reaches a 30, it start to sink. Okay, and when it start to sink, it can move in two ways. Okay, it can either come back towards the equator or it can go towards the pole. Okay, there is no, so the difference comes here, that in the one cell model it says that there is a unidirectional flow. Okay, it is going from equator towards the pole and the cold air is coming from pole towards the equator. There is no change or no mix up. But in the three cell model, it says that a warm air which is rising from the equator, it reaches the 30-degree latitude. Okay, it becomes cool, and as it becomes cool, its density drops. Its density increases, and hence it start sinking. As it sink, okay, okay. As it start to sink, it can move toward the equator or it can move towards the pole. Now the air which move toward the equator is known as trade winds. Okay, and you know the earth is moving towards this, right, from west to east. So okay, okay, so these trade winds move away from the direction of movement of the earth, and they and on the other hand, the air which move towards the Ferrel cell or towards the pole, they move in the direction of movement of earth. You see, so and they are called as westerlies because they begin from the west. Now this warm air which goes towards the Ferrel cell, it reaches this latitude which is 60, and again at 60 it becomes what, sorry, this cool air which is going from 30 to 60, it is dense. As it reaches 60 it becomes warmer. Warm air does what, it rise. So this rising air can again do two things. It can come back to Ferrel cell or it can go towards the pole. Okay. So if it come back to Ferrel cell, it becomes it form one cycle. If it goes to pole, it form another cycle which is towards the pole. Once it reaches the pole, it has the highest temperature. It has the lowest temperature because of cold air. Cold air sinks, it sink, and it moves towards the this direction. Okay, and this sinking air is moving from east to west, right? Because earth is moving from west to east, and easterlies are moving from pole towards the Ferrel cell in the direction of west. Okay, they are beginning from the east, that is why they are easterlies. Westerlies are beginning from the west, and the same cycle will repeat in the southern hemisphere. Okay, just a recap. Warm air means it has low density. Low density will rise. It rises, reaches 30-degree latitude. Okay, become cool. Cool air, high density, sink. Once it sinks, a part of it can come back towards the equator. They are called as trade winds in the direction of uh, away from the direction of rotation of Earth. A part of it can go towards the 60-degree latitude or towards the pole, that are called as westerly because they are beginning from the western end of the earth. Now this cold air which moves from 30 to 60 again becomes warm while it moves. It at 60 it becomes warm. It reaches up because of low density. Again it can either come back towards the uh, Ferrel cell or Hadley cell, or it can go towards pole. If it goes toward pole, it becomes cold. Now cold air does what it does, it sink. So again it will sink. Now it sinks and it moves towards opposite of the movement of earth. It moves from east to west, that is why they are called polar easterlies. Okay, so these are the three cell model in which the emphasis are that the uh, at each 30-degree latitude the air parcel has right to move in any direction irrespective of um, pole or equator, right? So this is the three cell model which currently we use in at present. Now the next question is about the vertical and horizontal motion of air parcel. Okay, so let's say this is a air parcel. Air parcel is, let's say, what we call is a 1 cubic centimeter ball. We can call it cubic centimeter. We can call it cubic meter area filled with air. Let's say a meter cube filled with air. Now it can move horizontally. It can move vertically. Okay, horizontally means that air is moving from point A to B. Let's say how to explain. Let's say a vehicle is moving and the exhaust from the vehicle is moving in the same direction horizontally. Okay, in the direction of motion. Vertically is when the air moves upward and how the parcel changes. Now, for the horizontal motion, two things which affect the motion is rotation and uneven heating. Okay, uneven heating because we know that the temperature Okay, we know that the temperature is changing, right? No, okay, I will explain it like this. So this is sun, and because of tilt in the earth, a region of earth is more exposed to sunlight compared to another, right? So the region which is more warm has different motion compared to a cooler region, and another is rotation. So both of these affect the horizontal motion. Horizontal motion, let's say on this plane, if I say air is moving from Africa, sorry, from America, South America to Africa, that is horizontal motion. So this horizontal motion is affected by the rotation, that how the earth is moving on its axis, and the which region of earth is more exposed toward sunlight. Why? Because sun leads to warming. Warming means warmer air, so the air in this region have low density and low pressure air, and on this region the air is high density and high pressure. Okay, so these are the two things which affect the horizontal motion of the air parcel. Another is the vertical motion. So vertical motion is dependent on the buoyancy and density. Buoyancy is uh, let's say a force which effect on a particle opposite to gravity. So gravity is this, a force which act opposite to gravity, which help this particle move upward. That is its buoyancy. And density, because as I discussed multiple times, that a colder air is more dense, and hence it will sink, and a warmer air or a hot air is can rise because of less density. Okay, so these are the different factors which affect the horizontal and vertical motion of the air parcel. Now, a very important force which actually help in all of this is Coriolis force. Okay, so this is a force which act due to the rotation. So let's say this is Earth, okay, and this is northern hemisphere, this is southern hemisphere. Now a parcel moving from this end to this end. This, I'm talking about horizontal motion here. Okay, so from point A to B, a particle is moving. Now, what this Coriolis force does is that because of rotation of the Earth, it moves the particle moving from point A to B towards the right in the northern hemisphere, and towards the left in the southern hemisphere. Now, how you can say is that if you know the thumb rule, okay, if you apply the thumb rule, you can see that the vector is in the right direction in the northern hemisphere, and the vector in the southern hemisphere is towards the left. So the Coriolis force which act on a particle in horizontal motion due to rotation of the earth, it moves the particle towards right in the northern hemisphere and towards left in the southern hemisphere. So uh, this force actually is very important. Okay, um, let's move towards other lecture, other questions. Okay, now we see the three cell, right? So from these three cell, what we understand is that the equator has more heat, it has more warm air, right? And what we understand from pole is that it has more cold air. So this is what happened, that there is heating in equator and there is cooling in pole. Now this actually depends on different heat flux of this air parcel. Okay, so the air parcel that we discussed in the previous slide also, it can have different way of transferring heat or of attaining heat, right? So sensible heat, these three different processes are sensible heat flux, latent heat flux, and surface heat flux. Okay, surface heat flux is when the radiation from the sun is actually warming the ocean. Okay, so the aerosol over the ocean, or the ocean, the warm ocean is carrying uh, the heat among them with themselves, and these ocean currents are the reason of heat flux. Okay, so we know about jet streams, eddies, all of that. So we'll discuss them in later classes, maybe in details. But for now, these ocean currents, these cold and warm ocean currents, we know the thermohaline circulation, right? Um, in the ocean. This thermohaline circulation is because of the warming and the cool water, and this warm or cool water actually can transfer the heat or the heat energy with the aerosol particles. Okay, so so the air over a warm ocean current is warm, and the air over a colder ocean current will be cold. So this is what surface heat flux is, that when these ocean currents radiate the heat to the aerosol particles in their vicinity, right? Latent heat flux is when latent means it's hidden, right? So when you don't know, when the particle does not necessarily show any sign of being warm or cold, but it has its, it can transfer the energy to the other particle. And sensible heat flux is in the atmosphere, these cells, these cell polar, Hadley, and Ferrel cell actually work on the sensible heat flux when the heat energy is transferred in the form of convection, conduction, and advection, right? So these are the three different way the heat can be transferred from one particle to another particle, and it leads to the equatorial heating and polar cooling. Okay, now before going to next question, when we discuss this the warming in the equator and the cooling in the pole, we know that we are making the pressure zone, right? So if we see on in a globe, near the equator, the it's a low pressure zone, and on the pole there it's a high pressure zone, right? So this is what we understood from the Hadley and polar cell, that the equator has a low pressure region and pole shows a high pressure region, right? So now how the air behaves in these uh, different zone. So this is what we need to understand, that what is the difference between this low pressure and the high pressure system. So low pressure means the equatorial system. So what happen at equator? Okay. Now, if the pressure is low, what we understand is that low pressure means low density. If anything has low density, what happen? The air with low density will rise. Okay, so in low pressure region, because of low density of air, the air start rising, the warm air will start to rise, and this warm air will move in the cyclonic direction. Okay, so if we follow the thumb rule, we see if the direction of vector is towards the up. Okay, if the air is moving up, then the circulation is in the what, in the clockwise direction, right? So this is what happened in the low pressure region, that the air or the pressure is inward in the clockwise motion. Or in the high pressure or the polar region, what happens is that it has high pressure means high density means sinking. If the cold air is sinking, then what happen, again apply the thumb rule. If anything is going down, then if you wrap your hand around, they are wrapped in the direction of anti-clockwise, right? So here the movement is uh, anti-clockwise in the high pressure region. Okay, the winds, the surface winds move anti-clockwise in the high pressure region, and they move clockwise in the low pressure region. Okay, so this is the difference, that because of the warming of the, because of the rising of the warm air and the sinking of the low air, the direction of movement of surface wind changes in the high pressure and the low pressure region. That is the major difference. It becomes clockwise in the low pressure region, and it becomes anti-clockwise in the high pressure region. Okay. So far we discussed about the general circulation. We discussed that how the change in the pressure causes the movement of air, how the flux affect the cooling and the warming in the equator and the polar region. Now, when we see atmosphere, there is different type of atmosphere, right? Atmosphere, like it's a very generic term, but when we start studying the atmosphere, we know that atmosphere can be stable, can be unstable, and can be neutral. Sorry. Okay. Now, next question is that only that how we differentiate between different type of atmosphere. Okay. Now, when we say these different type, we may, of course, we have mathematically derived these, but what we understand is that when the atmosphere is unstable, it means that there is a constant circulation, right? That atmosphere is not settled. There is constant upward motion and downward motion of the air particle. In stable, generally the motion is towards the down. Okay. Hence, we see the smoke, these photochemical smoke, these haze. Haze is one of the the stable atmosphere is one of the cause of haze, because it kept there is a lot of sinking of the aerosol in the stable atmosphere. In neutral, generally atmosphere is not neutral as such, but neutral is when there is no change in the atmosphere. It's stable, it's not, there is no upward and downward motion, like it's stagnant, the atmosphere is stagnant. So unstable means that, let's say we have a air parcel. Okay, if this air parcel, and this is outside air, if this air parcel is, let's say, 10 degrees Celsius, and the outside air is 8 degrees Celsius, what will happen? Because of its high temperature, what high temperature means, warm air, what it does, it rise. Okay, so it expands. So when the air parcel is warm or have high temperature, it leads to expand or the unstable atmosphere. Now when the air parcel temperature is less compared to the surrounding temperature, what it does, it sink. The air parcel start going down, and as it goes down, uh, below the atmosphere, it makes these haze or very concentrated layer in the atmosphere. Third is neutral. Neutral means that they have same temperature. The air parcel and the nearby air has same temperature. Okay, so there is no upward or downward movement of air. So these are the different type of atmosphere that we see around us. Now, before looking into the next question, I will move towards the next slide. Okay, uh, it's very important. Uh, okay. Now, this question is that we have to correctly match the following atmospheric condition. These are the different stability and neutral condition in the atmosphere, and these are the different plots. Now, before moving ahead, let's discuss the definition of these three terms. Now, these three are nothing but lapse rate. Okay. So, what we understand by lapse rate is that how the temperature is changing with respect to altitude. Okay. Change in temperature with respect to altitude is nothing but lapse rate. So, you can call it dt by dz. Change in temperature with respect to altitude or height. Now, there are different types of lapse rate. So this is uh, okay, this is saturated adiabatic lapse rate, this is environmental lapse rate, this is dry adiabatic lapse rate. Okay, now lapse rated, as I discussed, that it's the how the temperature is changing with altitude, right? Now, so environmental lapse rate is that at present, whatever air parcel is in the atmosphere, how they are behaving with respect to, or how their temperature is changing with respect to height in the atmosphere, right? Now, this is what we see. Okay, this is the, you can call it ambient, or this is the actual lapse rate that we observe in the nature. Now, what is, then what is SCLR or DLR? They are adiabatic lapse rate. So when we say adiabatic lapse rate, these are lapse rate that we discuss in the theory or in the laboratory. So adiabatic means, as the term suggests, that there is no transfer of heat. So when we say no transfer of heat, it means that, let's say this is the air parcel and this is the surrounding air. Okay, it's this, the temperature of this air parcel is 10 and the temperature of surrounding air is 8. Okay, so ideally, if this is not adiabatic, what will happen? The air will start to, will try to stabilize on itself. Wait, uh, hello, hello, can you see the slide? Okay, wait. Hello. Now is it audible? Hello. Hello. Yeah. Okay, okay. The screen is not visible, right? Okay, okay. Just wait a second. Hello. I hope the screen is visible. So I think this is. Did I explain the lapse rate before the internet issue, or shall I start again? This thing? Okay, okay, sure. I'll start again. Wait. Uh, okay. So this question is about the atmospheric stability, right? So here we'll discuss the lapse rate. First, to understand the atmospheric stability, we need to know about the lapse rate, right? So, what is lapse rate? It is nothing but how the temperature is changing with respect to altitude, right? So, or in short, it is dt by dz, that how with change in altitude how the temperature is changing. Now these three terms are here. One is SALR, ELR, DALR, right? So these are lapse rate. All of these are lapse rate. ELR is environmental lapse rate, or we can call it ambient or actual lapse rate. So this is the lapse rate that we observe in the air. So this is when there is air parcel in the atmosphere, how the actual air parcel is, like how their temperature is changing with altitude. This is ELR. This is what we observe. Now DALR and SALR are what we theorize. We make it in theory, or we in the laboratories. So DALR is nothing but dry adiabatic lapse rate, and SALR is nothing but saturated adiabatic lapse rate. Now their adiabatic lapse rate. So what does it mean? Adiabatic, adiabatic means that there is no transfer of heat, right? And when I say no transfer of heat, what it means, that if there is a air parcel with a with a temperature of 10 degrees Celsius surrounded by air with temperature 8 degrees Celsius, now this air parcel can either rise or sink. Since its temperature is high, it will rise, but what will not happen is that it will not neutralize, they will not neutralize each other to make a stable layer of, let's say, 9 degrees Celsius. This will not happen. Okay, so there will be no transfer of heat from the air parcel to the surrounding air. That is what it is called adiabatic. That when we are calculating the lapse rate in the theory or in the lab, we are considering that these each air parcel is actually an entity which is not transferring heat to its surrounding. Okay, so these are calculated or theoretized lapse rate. Now, based on these things, there the stability of atmosphere changes, and we have to see that which is which. Okay. Now, first is absolute stability. This condition is when in the previous also I discussed that stable means that the T parcel is less than T air. Okay, and if that is the case, it means that the ELR or the actual lapse rate should be less than the surrounding lapse rate. So it means that ELR should be low, and the DLR should be okay. So and in this case what happened, there is cold air and it's cold air which sinks. Okay, so it can happen when the DLR and SLR on either side of the ELR. Okay, so this should be on one side. So let's find a curve with ELR on one side. So ELR, okay, so these are two curves in which ELR is on one side of these two lapse rates, either above them or below them. Okay, now when it comes to absolute stability, which means that the temperature of parcel is less than air, it means it's cold. Okay, so the dry as well as the saturated adiabatic lapse rate should be wait did anyone okay, so okay, in a stable condition, the temperature of parcel should be less than the temperature of the surrounding air. It means that the air parcel is cold and it will sink. This will happen in any of the two situations where the uh, uh, ambient lapse rate is higher than the lapse rate of the what do you call the lapse rate. Okay, so this is example of absolute stability, that when the ELR is more than the DLR and SAR, so ELR is more than SALR and DALR. Okay, that is the condition of absolute stability. Now, instability we saw again previously. Instability means that T parcel should be more than T air. Okay, temperature of air parcels should be more than the surrounding air, and hence it leads to hot air and leads to rise of the air. When this happen, it means that the DALR, uh, SALR, so this surround the temperature of surrounding air is less and compared to uh, so these are hot parcel and these are cold parcels. Okay, so this is for the instability, that wait, when the ELR, that is the change in the actual or ambient temperature, is less uh, compared to the surrounding compared to the theory. So in theory the parcel are more hot, which we see that in the the parcel is more hot and they rise. In DLR and SAR the parcel are more hot, they rise. So this is a condition of instability. Okay, now, what is wet neutral and dry neutral? Neutral means that at least one of the either dry or saturated adiabatic lapse rate, one of them is equivalent to ELR, right? So, dry means that the dry adiabatic lapse rate is equivalent to ELR, and in wet, the saturated adiabatic lapse rate is equal to ELR. They are nothing but the RH condition. So if RH is less than 100%, we consider relative humidity less than 100% in the experiment, we call it dry rate. If we consider the relative humidity more than 100% in an experiment, we call that lapse rate as saturated lapse rate. Okay, now in neutral we say that either saturated or dry is equal to the environmental lapse rate. So these two curves are A and D, where ELR is equivalent to any one of them. Dry means that DLR is equivalent to the ELR. So this is the answer for D, that dry adiabatic lapse rate is equivalent to the environmental adiabatic lapse rate. It means that if, okay, is it not audible currently? Okay, okay, okay. Uh, okay. So, wet neutral and dry neutral means they are equivalent to the environmental lapse rate. These are the two curves which show it. For dry, it means DLR is equivalent to ELR, and the SALR is more than it. Okay. Uh, and in this, DLR is more than this. Okay. So, here the answer for A is this, that so here, if the parcel is dry, okay, there will be no movement because it is equivalent to the surrounding air. Its lapse rate is equivalent to the surrounding air. But if the parcel is wet or saturated, it will, this direction is hot, so it will rise. Okay. So if the parcel is wet, then it will rise. If the parcel is dry, it will not move. Similarly, in wet neutral, if the parcel is saturated, it will not change. If the parcel is dry, it will sink because this size is colder side for of the ELR. Okay. Now, conditional stability and extreme stability. Conditional stability means that one in one condition it's different, in another condition is different. Just the answer is C. For so ELR is in between. So if the parcel is dry, okay, it will sink. If the parcel is wet, it will rise. This is conditional stability, that it depends on the RH of the particle, that whether it will rise or it will sink. And extreme stability is a condition of inversion, which is B. That the lapse rate is, what should happen? The lapse rate should decrease. The temperature should decrease with altitude, right? The near surface temperature is hot. The near surface air is hot. As you move away from the surface, the air become colder, so the temperature drops. So ideally, the lapse rate should be like that, right? That with altitude, the temperature is decreasing, air becomes colder. Now, the ELR is showing a reverse trend. It means that the temperature is increasing. This shows increase in temperature. Okay, so this is the condition of extreme stability, and it leads to inversion. Inversion is nothing but when the air become a sandwiched air. Okay, that uh, a hot air is sandwiched between two cold air. So neither it can move up because it should move. The hot air should move up, but because the upper air is cold, with more density, it start to sink, and it makes this layer sort of structure with no movement in the atmosphere. Okay, that is inversion. So this is the condition of extreme stability. So to understand the lapse rate and atmospheric stability, these six floats are very important to understand. Okay, and now we move towards this question, that what are the different types of inversion. Now they will be discussed, I think, in further lectures, but in short, I will discuss it here. So first is radiation or ground inversion. So radiation inversion is nothing when if the ground is heated, then the so this is altitude, this is temperature, right? So ideally this should be like this. With altitude the temperature should decrease. Okay, so this air should be hot, this air is cold. Make, let's say I'll make this line, this is cold, this is comparatively hot. Okay, so ideally this should be the trend. But what happen is that because of ground radiation, the heat will transmit slowly, and it form these tiny zones of in between layers. Okay, so let's say this is hot air, so above it it should be cold, but because the heat is transmitting from the surface, it makes these sandwich layers between itself. Okay, so it becomes like this cold hot sort of thing. And again it's a condition of stability or extreme stability, and the air parcel will not move. Okay, so another is turbulence. Another is turbulence inversion, that if the nearby region is highly have lot of air coming in from all the direction. Okay, so it forms this again a stable condition of uh, hot air in between cold airs due to the turbulence or lot of incoming air. Subsidence is that if there is a industry, and industry have a very long shaft. Okay, now the this region uh, should be cold, and sorry, this region should be hot, this is cold, and this should be even colder. But what happened because of this, the release of shaft in this region become hot. Okay, so then this cold air become trapped between these hot regions, and this is called subsidence inversion, because it try to pressurize, but it cannot go anywhere because it's above. Hello. Okay, so subsidence is that, let's say there is an industry, okay, with a long shaft. Okay, generally the thermal power plant, they have very long shaft of kilometers, like 5 kilometers like this. So let's say near the surface the air is heated, so high temperature. As you go up, the air is cold. Now the shaft is here, it's releasing its pollution in this region. So ideally this layer should be cold, because as you go up the temperature should decrease. But because the pollutant are released in this layer becomes hot. Okay, and above this the layer is again cold, because the pollutant are released in the form of plumes, let's say. So these plumes will try to like disturb the above and below layer, but because they become this sandwich sort of structure, there is no movement in the downward direction and the upward direction. That is subsidence inversion. Okay, frontal inversion is that let's say this is land, uh, okay, and this is sea. So over the sea the air is cool compared to the land. Okay, so the cold air is dense, and the land or the warmer air is light, so it will rise. So it makes this sort of structure where it is a slanting. Frontal inversion is the only inversion which is at an angle. Okay, because here the cold air is here. Okay, so in this region, if you see this block, okay, I'll explain it here. Wait. So this is C. The cold air is coming from the sea, and this is warm. This is land. Land has warm air. So, uh, warm air rises, and here, if you see this region, you see these three lines. Okay, only here. This is warm air, cold air, and this is warm air, cold air, right? In this region, you see the cold air is above warm air. Um, so what they do is that it's a slanting inversion in which they basically over try to overlap each other, right? One sort of layer is it will try to overlap, and they make this sort of structure where partially on partial region cold air is over hot air, and then below this there is cold air, and in another region there is hot air, cold air, then this is again hot air. So on one side there will be hot cold hot, on the other side there will be cold hot cold, so it becomes this uh, yeah, this it's exactly that on one side, because this is at an angle, it forms a cold air hot air cold air structure, and on the other side it formed a hot air cold air and a hot air structure. So this is frontal inversion, which occurs at an angle. And last is valley inversion. Valley inversion is that so what valley inversion means is that because of sunlight, there is warming in the land, okay, and the land near the top becomes more warmer compared to land near the bottom, right, of the valley. So, and above this there is nothing. So ideally this should be like this, that hot air and at the top cold air. So cold air is there, but at downwards, because uh, there is lot of what less dispersion, and there is more radiation in a not radiation, I would say there is more transfer of heat from the land near the end of valley, near the bottom of the valley. So this region also become cold very fast, okay, and the region at the top of the valley receives sunlight, so it becomes hotter compared to the downward region. Okay, so this is valley inversion, that the toppest layer of the valley, which is near the top of the mountain, is colder. The bottom of the valley, okay, radiate heat very fast towards back to the atmosphere. It becomes cooler, but the slanting part of the valley, which receive the sunlight, becomes heated. Okay, so this is what valley inversion is, that there will be a middle layer of heated air. Okay, so these are different type of inversion. This is just a brief introduction. We will discuss these inversion later, in later lectures also. So for today, this is it. If you have any questions, you can ask. Anyone? Yes. Inversion, like what is inversion, or like what are the different type of inversion? Okay. So inversion is when okay, I'll show na just a bit. Okay, so ideally when we see troposphere, this is the trend, right? So this is temperature, this is altitude. With increasing altitude, there is change in or decrease in temperature, right? So this is hot air, and this is the cooler air. So this is the ideal scenario that should happen in an atmosphere. In inversion, what happens is that a sandwich layer becomes like a layer becomes sandwiched in the atmosphere, which leads to extremely stable condition. Okay, and we studied what is stable condition when the parcel sinks. Okay, when the T parcel when the temperature of air parcel is less than the surrounding air, and it will try to sink. Okay, so this is what stable condition means. So when a sandwich layer forms, that is, the this layer is hot, this layer is cold. Okay, ideally this layer should be colder than this one, but let's say this again become hot compared to the nearby region. So let's say this. Okay, so this layer it forms an inversion. I So what should happen? This should rise, but because a cooler air is sitting on top, it will not let it rise because it should sink. So they will cancel out. Now again, this layer should rise, but because a cooler air is sitting, it will not let it rise, and it will make a sandwich sort of structure. Okay, when this sandwich sort of structure is formed in the atmosphere because of uh, like sudden change in temperature, a stable atmosphere is created. This leads to inversion. Now inversion has different type. Ground inversion is when the inversion is due to the heating of the surface. Okay, so what it meant is that ideally this particle should be has highest heat. Okay, or is more hot compared to this particle, but because it takes some time to reach the heat to the particle, the this air is less hot compared to the above layer. Okay, so I don't have pictures here, otherwise it would be very good to explain it. So because the yeah, because the transfer of heat from the surface to the air parcel is not direct. Okay, it is very slow process. So it makes this sandwich structure, like tiny sandwich layers in the because of the ground radiation. Same for the frontal, when there is uh, land and sea breeze. So sea breeze is colder compared to land air or the warmer air, and it form this these sandwich sort of structure, where in this region this is a colder air, this is a warmer air, but this again um becomes colder air. So they make this um, structure in the frontal inversion. Okay, and in this region uh, so in this region the colder air is above the warm air, and in this region um, okay, wait. So they make this, how to explain, wait, this is land and this is sea. Okay, yeah, the best way to explain it, let's say this is land, this is sea. uh, Here there is a uh, industry, and it's making a plume. Okay, so this is cold, this is cold, this is warm, this is warm. Now this warm air is moving towards the cold, so this is warm. Okay, and this warm air from the plume will sit on this cooler air from the sea. So this form a inversion. So this the easiest way to explain, like study the frontal inversion is that, let's say there is a plume. The plume is emitting air in the direction of the sea, and this plume has warmer air. This warmer air come and sit on top of this cooler air. Okay, and above it, again this plume. After this plume, again there is a colder air on top. Okay, so again it forms a sandwich. Valley inversion is nothing but because near the towards the end of the valley, okay, the sun radiation, either they don't reach. If they reach, they radiate back like very fast. So the downward region of valley is cold. The top of the valley is near mountain, so it is also cold. And the slanting region of valley is actually hot because the air, because the sunlight directly falls on this. So they make again a sandwich of hot air, cold air, and cold air. So these are different type of inversion where, so in simple terms, inversion is nothing but when uh, a different type of, let's say, uh, um, when a hot air comes between two cold layers, or a cold layer of air comes between two hot air, that is what inversion is. That when the movement of air becomes stagnant. Okay, that is it. In the next class, what I will do is I will put some pictures and then I will explain this inversion again. Okay. If, yeah, if anything else, if you want, anyone. It should, because I am making these questions on the based on the lecture series itself. Uh, but I don't set the question paper, so it depends on sir. But I'm trying to include as much as information as it's given in the lectures. So let's see. Oh, yeah. Uh, okay, so if no one has any questions, we'll end this session today. And thank you so much. Yeah, I don't have any tips on this. Like how can I give tips? If you study well, I think the important thing is that if you go through lectures, I think that will be enough. You don't have to follow any external material for this. I am sure for this that. Okay. Okay. Yeah, that's great. I think this subject also you will crack, so no worries. Study well. Um, yeah, yeah. Okay. So thank you everyone. Let's end this meeting here. Okay. Thank you. Thank you.